So welcome everybody. I want to talk a little bit about where we are in wireless communications and do we have a future? Yes? And since I'm a professor and I have PhD students, and it's, by the way, it's totally fine to take pictures or videos or whatever you want to do. If you're a PhD student in my team, you should be able to ask me as your professor, are you working on the right topic? Yes? Is there a future for myself? Am I just doing my PhD in a topic because it's fun and 5 years later there's no future in this topic? Which can happen. In this case, I think I would like to talk about something where I truly believe we still have quite a bit of a future. So just to give an idea where I come from, I'm Vodafone Chair Professor in Dresden, which means I'm actually, this year it's going to be 25 years funded by Vodafone. The only Vodafone Chair Professor, as far as I know, on planet Earth at this time. And Vodafone headquartered in London has an academic thing in Dresden. This is obviously has a good reason because it used to be Mannesmann, before Mannesmann was bought by Vodafone. And also the idea was to help out East Germany. So Dresden is a former communist in East Germany. And so the whole idea was to start out something bigger. And these are companies that sponsor my work. And these are companies which we do project partners, and obviously we've done quite a bit also on startups. These are the startups so far. A whole bunch of startups. Some of these startups started another startup to start the startup, because in East Germany people are poor. They don't have money, they didn't inherit money. The wall came down, there was no money there. And to be able to start a company in Germany, you need 25,000 euros capital. You have to put in the bank. And not everybody has parents that have this money. So we, for example, in the first cases, we did this by participating in business plan competitions. Yes, and so you write a business plan, you submit it, and then you get the first prize, you get 10,000 euros, and then you're almost done. Because you only have to, your liability is 25,000 euros and your cash that you have to put in the bank is 12.5. And so, for example, Signalion, we wrote a business plan on industrial radio. We wanted to build a wireless internet for robotics. And that was our business plan because we thought this is exactly hot at this time of when the competition was there. Yes, we got that, and then we built a company doing something completely different. Yes, and we did that quite a few times, but other cases also, for example, here, these guys started climbing the Kletter Arena in Dresden, where it still is very active. These guys started a liqueur company, and so liqueur in every second bar in Dresden, which still today is very successful. So that's what the whole thing is. It's about coming up with funky ideas and doing things. Some of these startups were sold. So obviously this company, just to give an idea, one of their main products is the Icarus modem. Icarus is a big project funded by Germany, trying to do bird tracking. So the base station has been launched on ISS beginning of last year. And the wireless modem, the trackers, are 7-gram big things that are clipped on the back of the birds, here in the neck. And then we can track them for 9 months up to 12 months and see which migration paths birds take. Cool things like that. And 7 grams is battery, modem, antenna, packaging, everything. And how you do something like that with multi-carrier spread spectrum, in this case, to do that. The Consolid is an urban IoT company, chip company, and if you have a phone from this fruit company out of Cupertino, starting with the iPhone 7, the 4G modem comes from us, from Blue Wonder, that we sold to Intel. Now, if you talk about 5G, the idea is bigger than just building modems. And so that's what I did is I called out in Dresden and said, how about starting a bigger kind of thing? And why is it bigger? I'll tell you in a second. And so all these different colleagues of mine joined, and Frank Fitzek and myself, we co-lead this. And Frank Fitzek has the telecom chair, I have the Vodafone chair, and jointly we lead 5G Lab Germany and bring this hopefully forward. The idea is a little bit copycatted from the US. So a good idea, why should we take them? Saying that we ask companies to fund us with at least 100,000 euros per year. And so we have 18 participants, and we get more than 3 million euros a year out of 18. So that shows you that not everybody just stays at the 100K level. And we have a couple more, 3 more in the makings right now. Klaas, Bosch Rexroth, and yet another one. Now let's talk about the future. If you want to talk about the future, it's always good also to look in the back mirror. 1G was something starting in the 80s, which was analog cellular telephony. And this analog cellular telephony was about voice. And it was very clunky. 2G made it happen. 3G was about mobile internet. 4G made it happen. 5G is about mobile robotics, the tactile internet. And most likely we need a second generation to make it happen. Now, what does that say? Could we have scrapped 1G and right away gone to 2G? No. We're engineers, we're humans, we have to try out things. Yes, 3G was probably the most costly experiment on planet Earth from a communications point of view, with wideband CDMA, a very bad idea for wireless cellular communications. But Qualcomm and the likes taught us this is the best thing since sliced bread. We tried it out and found out it doesn't work. And so we did something different using OFDM with 4G as a community. So 5G obviously was super fast, put together because of the Olympic Games in Tokyo next year. It should be up and running by that time. And the Olympic Games last year in Seoul, in South Korea, there were supposed to be first demos there. So for that reason, it was put together very quickly. Now, if we talk about that, the question is, what is the future? Where can we go beyond? One is obviously we can talk about massive data rates. So data rates have been increasing about 2x every 18 months, 10x every 5 years. Doubling every 18 months, Moore's law. And this is very simple. If you take your phone, you buy a certain amount of flash memory inside, and the percentage of your memory that you want to push back and forth stays about the same. The memory size increases, so the data rate has to increase as well. This has been true for Wi-Fi, this has been true for cellular, with about 100x difference, and then somewhere around this time frame, 2008 or so, the Wi-Fi growth has slowed down a bit. I think one of the reasons is because people are lacking applications. Yes, what is this additional data rate good for? And Wi-Fi was just growing too fast. Now the question is, are there applications? And I think yes. If you just look at video, virtual reality and augmented reality, these are applications where if you really want to get rid of this cable, where my poor PhD student Tobias Katur is currently connected here with a cable, if you want to get rid of that cable and really build a nice 8K screen on the right and left eye at low latency, what you need, then we need around, in a compressed video case, around 100 gigabit per second with today's compression technology. 100 gigabit per second obviously is more than we have, so we need at least 1 terabit per second to be able to deliver 100 gigabit per user. So the good news is there are applications out there that really need vast amounts of data. The bad news is we're sort of in a situation where people think it's slowing down, maybe, and we have to reach somehow into the 10 to 100 gigabit per second for these applications to really work. This is according to what Disney Studios, Facebook, Oculus, the Google VR AR team also tell me, I met with them 3 years ago in Los Angeles, had a whole session with them, and they say AR, VR could really take off if you wireless guys finally had an interface that was fast enough. If we want to go to these high data rates, obviously one of the big challenges that we have, if we go look at that, is power consumption. Yes, if this is my base station, and I'm standing here, and this base station is sending out a signal with a certain power level, here I have a signal to noise ratio. Now I want to increase the data rate by 10x. I have to increase the power by 10x to have the same SNR per bit. That's a challenge. So what do? Instead, we move closer to the base station. Yes, we about half the distance to the base station, and so then we have also a tenfold receive power level increase. So we can densify networks, we know that, that's okay. However, where does the power consumption then lie? It lies in still the analog digital converter. Because even if the power amplifier stays at 100 milliwatts, and the low noise amplifier is sort of in the same range, whatever, all, we are, as currently, obviously wider band and whatever, but currently, we will not increase the power consumption of the RF so much, but the analog digital converter that we have today, for example, if you want to do 30 gigs bandwidth signal, we're talking about at a reasonable sampling rate, a little bit oversampling. There are A to D converters for wireline systems, super low power, 120 gigs, 30 gigahertz bandwidth, 500 milliwatt. If we say not for 30 gigs, but maybe 300 gigs bandwidth, which is a terabit, or at least 100 gigs, then we're talking about 5 watts. And then maybe massive MIMO, a couple antennas, in phase and quadrature phase, we're talking about 10, 20, 30, 40, 100 watts. So this is the big challenge, the analog to digital converter of our future, if we want to do high-speed transmission systems. So let's start understanding a little bit about system theory and look into that from a point of view of what can we do. And if we look at it, we have learned once upon a time that we do sampling according to Nyquist theory. And this is an equidistant sampling normally. And if we sample fast enough, twice the bandwidth, we can reconstruct our signal. This is not quite true. We cannot reconstruct the signal because we also quantize the amplitude. We get quantization noise due to that, but the quantization noise is not such a big problem because we make sure that we have enough quantization level for the quantization noise to be small compared to thermal noise. So this is how we have been designing systems. And if we increase the sampling rate by 2, we increase the power consumption of the A to D converter by 2, more or less. What is the problem? One of the big problems is the further we go down to deep submicron silicon, the voltage swing that we can do becomes smaller and smaller, and our automatic gain control can make sure that our signal exactly fits into the span of our A to D converter, of the quantizer of the A to D converter, start eating 70–80% of the power. So instead of doing that, we could also go and have the same amount of quantization steps with a 1-bit ADC. We can get rid of the AGC, automatic gain control completely. A 1-bit ADC is the simplest level sensor that we have. That's a dramatic change. And just oversample 1-bit. Obviously, this means if we look at that from an amplitude point of view, we have zero information on the amplitude. All that is left is where does the zero crossing happen. So basically we have to build modulation schemes where we design them such that we define where the zero crossing happens. So that's why we call this zero crossing modulation. It's a little bit like disk drives where you sort of have only the one or the other magnetic polarization of your material. Here, obviously, it's a little more tricky and interesting because we can actually do faster than Nyquist signaling. We can do all kinds of complicated things to make sure that we get an information theoretic capacity that is big enough to be able to address the needs. Good news, this works. This works also in the lab. And we set up this little demo here. This is at 300 gigahertz carrier frequency, obviously a little bit higher than what normally people do these days. But for these bandwidths, we need to go to higher frequencies. And we can see that we can actually get things to work. And gain a lot in power consumption. Having said that, we know 5G is going to be delivering 1 gigabit per second. Maybe its next version, 5.5G, 10 gigabit per second. But we actually need 100 gigabit per second and beyond, so we need to come up with that. Next challenge is reliability. Reliability is something that has been around for nearly 60 years now, in 50 years, let's say. It's basically, reliability theory is a theory, a mathematical theory that was created and invented in the 60s, mainly for the moon mission. And the idea is, I want to build a system that is reliable to be able to survive the moon mission. And then it was applied to airplane design, car design, and everything else thereafter. So the key performance indicators that are in reliability theory are very different from what we know from wireless communications. It's about probabilities and it's about time durations. If I go to a factory automation guy like KUKA Robotics or ABB Robotics, they tell me, I want a wireless link to be so reliable that at most it has a packet error rate of 10 to the minus 9. 10 to the minus 9 means 3 seconds downtime per year. That's how they look at it. However, nobody is going to run a robot 24/7 the whole time without any maintenance and any intervals at all. So it is about the probability not only of being available and being reliable, it's about also the time duration, and so what we really have to look at is interval reliability. And that is a very different case than what has been done in standardization in 3GPP. And so if we look at it from a point of view, this is experience that we have gained now over the last couple of years working with KUKA and Franke Emika, two robotics companies. Is that they look at this really in a complete different way. Now, how do they look at it? A KUKA robot stops after 3 contiguous packets are lost, and a Franke Emika stops after 5 packets in a row are lost. Why is that? Well, once upon a time you learned automatic control. Yes, in some kind of a course, control theory. And what you learned is that you always sample in a control loop much higher, sampling rate is way higher than the loop bandwidth. Every PID kind of controller always has a loop bandwidth that is way lower than your sampling frequency. And so losing a packet once in a while is not going to kill your control loop. Losing 2 packets is not going to kill your control loop of a KUKA robot. 3, it's going to be a problem because the loop bandwidth is designed that way. Here the loop bandwidth is designed that you can actually lose up to 5 packets. So what does that mean for us? That means for us that we can actually go and look at the wireless channel in a different way. Because if we look at the wireless channel over time, we lose it once in a while. Yes, we have deep dips, the fades. And these fades mean we can lose a packet, then we repeat. No. So this is how things are done in 3G, 4G, 5G. It's called hybrid ARQ, automatic repeat request. Yes, if you lose a packet, you transmit auxiliary information, additional information to be able to reconstruct that packet. But this is not how a controller works. A controller works, if I transmit these packets, this has to be for the next sample. So this is not hybrid ARQ, this is a new kind of input from the control loop. So then we could, for example, double up over 2 parallel channels to make sure one of them makes it. If both don't make it, then we can quadruple up. Yes, get 5 times, and we have to make sure that then at least one of them makes it. And then we're fine with our, for example, the KUKA robot case. But if you look at this, this is sort of almost like a trumpet. So we get a cocktail party effect. As soon as one robot loses its piece of communication, its link, we suddenly have an increase in interference because it will start communicating more and more and more and more so. And so we have a big challenge. However, good idea, but we have this cocktail party trumpet effect. And then if this is to go talking over 5 times as many resources, it's going to start killing other communication links of other robots, and they will start trumpeting up, and everybody tries to scream louder and louder, and then nothing works anymore. So what have we learned if we know about Rayleigh fading channels? I tried to keep this as simple as possible in my talk here. In a Rayleigh fading channel, we know if we have a diversity 1, we have an SNR increase of 10 dB and a drop in packet error rate of about 1 order of magnitude. If we have a diversity 2, then we have exactly twice the drop in the logarithmic level. So we go from 1 to 1%, and from 10 to the minus 2 to the minus 4, with 10 dB increase in SNR. If we have diversity 3, we can triple the steepness, 4, we can quadruple the steepness. Which means actually I can do the trumpet that I mentioned before. However, I don't have to keep the signal power as strong, because if I have diversity 2, I can actually, to be able to have the same packet error rate, I can reduce the signal power dramatically. Now this, however, means if I do that, the current standards are not designed for that. Why? Because then you lose synchronization. Your pilot power is not big enough for the other side to be able to reconstruct the channel, do the channel estimation, carrier recovery, timing recovery. So then we have a big challenge. So we need channel estimation synchronization to function under these circumstances, which means obviously that the way modems are designed today and standards are designed today, that there are some people that work on making sure the data works and others work on pilots and synchronization. Those are over. We have to combine the two to really tackle this challenge. But then we can. Next topic, control. If we then do this, obviously we cannot only tackle this single kind of robot, but do max of control. So this is basically the idea of going to the tactile internet. Yes? What does that mean? If I throw this object to you, it travels at 10 meters per second. That's what if I would throw my phone to you guys, that's sort of the speed. If you want to catch it with 1 centimeter precision, at 10 meters per second, that means 1 millisecond precision. So the way we interact with our life and actually try to balance a ball and catch things and do things, we want our environment to act around the 1 millisecond speed. By the way, that's also the reason why you get sick to your stomach when you put on virtual reality goggles today. And that's one big challenge I was pointed out by Disney Studios guys. So if you do a 3D movie today, you would have a big cleaning job in the cinemas if they wouldn't do a trick. The trick that they do is, as soon as you jump you would get sick to your stomach if they wouldn't make the side of your vision foggy, because the systems, what is it, the picture frame rate is not high enough for you to feel comfortable. If we look at a TV in front of us, it has 100 Hertz frame repetition rate, and that looks pretty smooth. Because here in the center of our vision, that's exactly the resolution we need. We have a high color resolution, but low time resolution, only of 100 Hertz. If we go to this side, I can see my hands now, but my hands are more or less in black and white. But it turns out the time resolution out here is a kilohertz. So if anybody of you ever goes and does an eye test for a PPL license, for a private pain license, it's fun, I did that. You can actually test your eyes, and in the eye test you notice suddenly that sparks that you cannot see in the middle anymore, you still can see on the side. The resolution is higher and your reaction time is much higher. So if you want to make sure that you know the next sparks are coming in the middle, you just have to look to the side and then you can quickly see those and react and push the button. And then your eye test is much better. So this is really interesting. What does that mean? In other words, we have to be able to build our systems all the way down to 1 millisecond reaction time. In 5G, we are now going to be around 5 milliseconds, and going down to 1 millisecond is important. So if we then have situations where, for example, this is our input device and this is our output device, so this is our remote control input. You see here an antenna, here you see an antenna. These two systems are connected with our own modem that we designed that has less than 1 millisecond latency. Sort of a 5G kind of system, but with our own funky little tweak to it. Now I can take this and steer this, the idea is to steer this ring around the 5 and don't touch the 5. So here you see me. You see me sort of trying to move it over this 5. Obviously, I'm not perfect. Yes, I did touch the 5 once in a while, but you can actually feel, you get haptic feedback, and you can sort of move this and get something done. And to be able to do that with fine kind of motoric feedback and seeing what's happening, we need to go down to 1 millisecond. And for high-speed robotics in factories, we have to go down to 125 microsecond reaction time, latency. If we do that, it's cool, a ton of new research challenges. But is that it? Nope. We have forgotten something completely, which is resilience. What is resilience? Why do I show factors here? So one of the ideas of the Tactile Internet, this wireless robotics infrastructure that we will have, is to be able to connect everything together, and we can jointly do this in a robotics fashion. There's one guy sitting in one of these tractors, and everything else is done automatically controlled. The drones fly automatically around, make sure we're not seeing a deer or whatever, everything's fully automatic. But so the same thing in the factory. So instead of having a million remote controls, this whole thing is going to be done via the infrastructure. Then we have the factories. Every factory wants to have their own little 5G tactile internet. Yes, we are currently, we can watch if you fly to Dresden, you can look out the window, there's a big Bosch factory being built right now. Bosch's biggest investment in its history, the 1.3 billion euro chip factory for their Bosch process, the MEMS process. And they want to build their own 5G network. And the next factory next door is Global Foundries, and you have Infineon around the corner, and you have AMTC around the corner, and everybody wants to do their own factory with their own network. Every farm as well. If that happens, what do we have? We have one wireless premises network, and we now get three new challenges. Because currently, if you look at your phone, it tells you, now this guy doesn't tell me anything because I'm in EduRoam, but it tells me what kind of network operator I'm in, yeah, Proximus, for example. And this means when I go to the German border, the German operators and the Belgian operators have to talk to each other and coordinate how to use those frequencies at the border such that they don't kill each other's networks. The same thing on the French border, the same thing at the Dutch border, at the Luxembourg border. Not so much at the North Sea because England is far enough away. So we have a wireless premises network, however, now, and not a clearly designed border because everybody sets up their own wireless premises network, their own private 5G. That's part of the idea. This means we have another guy setting up its wireless premises network in a neighboring system. However, these guys start interfering, and these are not, you cannot start having everybody talk to everybody and say, you stay out of my frequency, I stay out of yours. It's impossible. So this means we have a massive interference challenge coming up. Then, in this network, we have terminals. And these terminals generate interference as well. Meaning it might have a non-line of sight to the base station, but a direct line of sight with a very strong receive power to a terminal sitting here. And this terminal doesn't hear its base station anymore because it's completely dwarfed by this terminal. Yes, the low noise amplifier saturates, off you go. So this is unintentional interference. And finally, we can have intentional interference, yes, because you can go out, you can buy for 156 euros a GNU radio today. You buy for a couple dollars a 30 dBi antenna. You download a little bit of Python code or write it yourself. You build a little bit of a frequency scanner, find out the space station over there. I don't see an antenna right now, but let's assume that flagpole was a base station over there. What is the frequency? I can find it, and I just send a nice CW, a nice cosine signal, and I saturate that low noise amplifier, and that base station is dysfunctional. I can do that today. Everybody that's sitting here can do that today. But it's no fun. Because then you have a dropped call, internet doesn't work for a little bit of a while, and people think, oh, network is not there. But if those are tractors on the field and robots in the factory, and you can suddenly see the robots start smashing the cars or the tractors falling into the ditch or whatever all, then it might be more fun for hackers to start doing that. So we have to be able to build a cognitive radio aspect in here to scan the situation of the network and react continuously. This was completely forgotten in standardization. Is there research that has been done on that? Yes, a ton of research has been done in Belgium, in Germany, and other places on software-defined radio, cognitive radio, and everything. So it's not that we don't know how to do these things. Let's say we don't know how to do these things such that it happens automatically. But here we are in a situation where we will be able to address this, and this is yet another new gigantomanic research challenge that we have ahead. Then let's talk about scalability. If we look at scalability, obviously we have the challenge to be able to address a big range with 5G. We have a latency of 1 second, all the way up to 1 millisecond. 5 milliseconds in its first version. We want to do 100 kilobit per second voice calls, all the way to 1 gigabit per second data to start out with all these different applications. Yes, the clunky AR, VR with these low resolution goggles of today, automatic driving, video streaming, etc., 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 sitting in this plane. Now, if you look at this plane, this is about 3 orders of magnitude in latency and 5 orders of magnitude in throughput. So this is 8 orders of magnitude in terms of computational power. If I look at the 3 chips that are being designed right now from HiSilicon, Samsung, and Qualcomm, they're sitting up here. Yes, they're supposed to be for the new high-end phones. They're going to have to be able to do 1 gigabit per second at a fairly reasonable low latency. Now, you're not going to do automatic voltage and frequency scaling over 5 and plus 3 over 8 orders of magnitude to build the right solution. When the boxes were in 2G, 3G down here and 4G, it seemingly still was the case. But even in 4G not already, because in 4G already we built a narrowband IoT modem sitting down here. A specialized solution with ComSolid, for example, our startup. So the question is how to be able to address this space such that we can build a scalable solution. So we need a way to design this beast and then don't have to redesign everything to address this market, for example, industry, automation, or market down here for video streaming, etc., etc. So we have been working on this in my team with a whole design roadmap since quite a few years of how to build these scalable solutions. Good news is we've been working on this, and others have been working on similar ideas. So that's cool. That's yet another big, gigantic research challenge, is how to build chip architectures, multi-processor system on chip architectures to build these scalable solutions. Okay, next problem. Sorry, I'm just trying to tell you why there is so much fun in doing wireless communication research. Rural deployment. I mentioned, if I want to talk to that base station 10 times faster, I move half the distance. That's true in rural in urban environments. In rural environments, it turns out I actually have to go to 1/3 of the distance. So I have to go 3 times closer. The result of that has been that we're losing more and more of the people in terms of having internet access. So if you look at the news and at what has been written, about 3.5 billion people have wireless internet today. With 5G, this number is going to drop. Because why? If we define broadband internet, 20 years ago it was 384 kilobits per second. If now I have edge in my display and it says 384 kilobits per second, I cannot even open the Google search web page anymore because the data that I want to get down there is too big. Doesn't react. Yes, you can open the German regulators web page, you can open all kinds of web pages also with Edge, but modern web pages don't function with Edge anymore. So as we increase the capability of data access, the internet becomes fancier, people get used to it, and we're losing more and more of the people. So how to connect the remaining 4 billion people? So we have to be able to build systems where we can address large cells again. And I can give you a whole 1-hour talk on that as well. Ideas and research results and how this can be done. But I just want to give you a glimpse here. Obviously, if I go and build a cell that is 50 or 100 kilometer radius, what is the problem? Delay spread. Yes, delay spread is fantastic for us wireless engineers because it's basically the reason for it is the speed of light is so slow. It's only 300 kilometers per millisecond. So which means that one single bit of GSM is only 1,100 kilometers, 1,100 meters long. Yes, and if we build a gigabit data pipe and build serial bits behind each other, each bit would be only 30 centimeters long. If it's only 30 centimeters long and an echo off that wall talking to you and then a line of sight, the interference is such that multiple bits start being delayed and interfere with previous bits, and it's a big mess, and we have to build a nice equalizer, channel estimator, equalizer to get the thing apart. So what is the idea? Instead of making these bits very short, we stack them on top of each other. This is called orthogonal frequency division multiplexing. So in time, we make the symbols long but narrow, and just stack many of them so that we can use an FFT to generate such a symbol. And then, obviously, the symbol is corrupted at the beginning when everything starts and at the end. And to make sure that that doesn't happen, we basically do something called a cyclic prefix. We take the latter part of that symbol, copy it up front. This is what we call the cyclic prefix. And then whatever comes from the previous symbol is just messed up in the dark blue part, and the light blue part is not corrupted by the previous symbol because we make sure the cyclic prefix is long enough to make up for the distance in path. That's the basic idea of OFDM, blended externally normal. However, where's the problem? If I have a 100-kilometer radio cell, my delay spread is at least 10, maybe 30 kilometers. If it's 30 kilometers, that's 100 microseconds. That's a huge amount of time. If this is 100 microseconds, then this guy is also 100 microseconds long. This has to be at least 10 times larger for this whole thing to be efficient. So my symbol is already in the millisecond range. If one single symbol is 1 millisecond, there's no way I can do an end-to-end 1 millisecond tactile internet. The packets have to be short. The other challenge is the longer I make the cyclic prefix, the longer I make the symbol, the closer these subcarriers become, and then the phase noise of my oscillator is going to generate inter-carrier interference, and I cannot get this system to run. Yes, even with modern day oscillators, we now have a subcarrier distance of 15 kilohertz in LTE and 5G, which is pretty much at the boundary of what is reasonable to have cheap oscillators running their systems. So what is the alternative? The alternative is what we do in the 4G and 5G uplink. We basically do these very short symbols. Each and every one is very short. Again, we take the latter part of this, we move that up front, and we do frequency domain equalization. That's a technique that can be done. However, if we have all these different applications with this 8 orders of magnitude, it's a mess putting this into this kind of a system. Because we have to have multiple guys sitting in frequency space and time space somewhere. So what can we do? If this blue stuff is too big, we can actually just say, let's use the idea of a good old Hungarian mathematician, Gabor. Yes, he came up with the idea of taking not only time, not only frequency, but actually doing what he calls the Gabor frame, taking time and space and frequency and looking at it as a system like that. So instead of subdividing it in time or only in frequency, I can do a combination of both. Then now suddenly I have simple blocks per subcarrier sitting behind each other, which means I can do filtering, like a circular filter. Then I can take this, I can copy the first part up front, cyclic prefix, and I'm there. Now I can build systems that make sense. So that's why this is important for very large cells, where we have to tackle this in a reasonable way, such that we can make these systems happen. Finally, another topic, not finally, but I think I still have two topics. One of the last topics, security. So if we look at the security and we want to make sure that this kind of system happens in future, yes, we want to have automatic driving. Not autonomous driving, that's not quite possible, automatic driving. So we are a human being, we have a virtual bubble, yes, or a personal bubble it's called in America. Don't touch my personal bubble. A virtual bubble. And the cars just start driving around. We don't need any traffic lights anymore. And as we walk, our personal bubble secures us so that we're not hit by any car. And even if we install the right cameras, we can see objects that have no tag, like a frog, and it happily crosses a street and is not killed when it walks from A to B. If this is the case, obviously, what do we need? We need to know the position of everything. We need the vision of a human, of a car, of everything. And if this something is Monsieur Barroso or whoever it is, it might not be so nice to that person because everybody knows where they are. And one of our startups, RadioOpt, we built a traffic monitor app. One of the first things that happened is the CEO of Vodafone downloaded it and tried it out, thought it was cool. And we could see by 1 meter precision where he is. So right away, of course, we're in Germany, so I got a data privacy agent right away into the car and said, this is not good. Yes, so that we anonymize it at the creation point so that we cannot have access to any personal information. What does that mean? We have to be able to build these networks in a different way. Today, if this terminal is a car, for example, and you have WhatsApp and Facebook and Google and whatever kind of apps on your device, anybody knows where you are. You talk to the base station it talks to the edge cloud, and the edge cloud is sitting there, and in the background you have the cloud. So what we really need to be able to make sure is that we have to make sure that this part becomes private. Because the edge cloud controls the cars. It needs to know exactly the weight, is the person authenticated, everything. Edge cloud needs to know everything. That part of the application. But hopefully the cloud knows hardly anything. It just knows there's an object that's moving and that's it. For traffic planning. So that means we need to be able to put in some kind of a barrier skin. Now, don't take this as something physical, something sitting exactly there. It's just a metaphor for something that we have to create. So the question is exactly how to create that is a big open issue. But some kind of a barrier skin so that we can ensure that privacy is held such that terminals are secure. And if this privacy is held, that terminals are secure, the next thing we have to make sure is that this terminal itself is secure. And with Spectre, Meltdown, everything that we know terminals are not secure. Why? Because current multiprocessor systems have shared memories, caches, which is a shared memory, and as soon as we have that, things are insecure. So we have to make sure in the second stage that we also have the right hardware, operating system, software platform sitting here, such that we can ensure that the operating system orthogonalizes threads into different parts of hardware, such that we can really make sure that the hardware and the operating system cling together, not like now. Now you have certain people that design x86s and other people design secure operating systems on top. There's only one single company that does a combination of both, which is Amazon Web Services. They design their own chips and their own operating system and try to build for their own system a solution. The operating system is 100% designed by the team in Dresden. They're growing right now to 400 people, where they're doing the whole operating system design for that. So we need the same thing in the edge cloud, and we need to make sure that the same thing is available for the wireless part. Yes, will we have 100% security? Never ever. Most likely not. But at least at a level where we feel more comfortable than what we have today. That's the reason why we started the Backhausen Institute last year. Ingrid is heading the scientific advisory board to really make sure that we address this challenge, not holistically, just adding little sparkles where we think we can add our little bit of knowledge. Don't get me wrong, because as I mentioned in the opening, we probably would need 9,000 people to really tackle this. That's more like an Oppenheimer project than so it's really coming up with the right research solutions and ideas to provide something such that we can trust our systems of the future. Now I want to come to yet another story or challenge ahead, which is the energy efficiency. So this is, for me, very interesting, because I'm to blame for one thing. In 2007, data was produced that was made available in 2008. In 2008, I started looking at this data and saw that the energy consumption for ICT, information communication technology, is increasing such that by 2020, next year, ICT will consume the complete power grid of the world, just to run ICT. So I started a research program of 160 million euro volume by German government, funded by German governments. We call it Cool Silicon, to build energy efficient electronics. And we talked about that, and then the European Commission started all kinds of different energy efficiency projects, E2R and whatever they were called, as well, and I participated in many of them, trying to make sure that we get this curve to stop, because it was increasing dramatically. Now what happened is industry reacted very quickly to this, because in 2007, for example, telecommunications operators spent more money on the energy bill than on personnel costs. Yes, I said that's an easy fix, just give the engineers a nice hike in salary, and they didn't like that idea. Anyhow, so what happened? People really sat down and started redesigning data centers more efficiently. And so what you see, things have been flat since then. And so everybody, now these days, nobody talks about energy efficient electronics anymore. That's done, that's solved. But that was 2014, when these hindsight projections were done. And now new data is coming out with the 2017, 2018 analysis, and this is the forecast. Okay, so everything stays nice and flat, and this is 5G, and this is data centers. Okay, so we see that data centers are supposed to go from 200 terawatt hours to 3,000, and 5G networks from 300 terawatt hours to 4,000. It's super interesting and scary. Yes. Just think of it. Why? I talked about the edge cloud. Yes, we need the edge cloud to be able to run a nice latency efficient application. We cannot go from here to Paris for a server sitting there to control the car here. Not because of data integrity, just for latency. Speed of light is too slow. 300 kilometers per millisecond. Going to Paris back and forth is already 10 milliseconds. So we need the edge cloud locally, and the base station and the edge cloud servers with the new Intel chips are so nice that people are building the base stations not with hardware anymore, but just software on a commercial off-the-shelf server chip with a new edge cloud server chips that have forward error correction accelerators and some cipher accelerators and whatever else built inside. Nice. However, these beasts consume power because the applications are all over the place. And the other part is we'll have high performance computing in a box all over the place. Just think of it. If you have a Tesla, just your NVIDIA engine running your automatic drive consumes supposedly 1.5 kilowatt. Okay? And if we were to linearly scale this to really do autonomous driving, then we would be talking about 20 kilowatt, which is exactly 1 kilowatt more than the Tesla consumes on average, 19. So automatic driving would double the fuel that is needed. So we have embedded high-performance computing applications coming along all over the place. If we robotize the world, it's going to happen. So the cumulative average growth rate for these kind of embedded high-performance computing is seen to be around 17%, and similar in the edge cloud business. And so the question is, this growth is fantastic from the person that is selling this stuff, but it's terrible from an ecological footprint point of view and as well as from a rollout point of view. So how can we grab a hold of this and make this more efficient? So what I started looking at the 2007 numbers, not knowing that it would be flattening out, is a big research center already at that time, also on highly adaptive energy efficient computing. And so instead of having server chips on a printed circuit board like that, connected with copper wires, the idea is to say, let's build some interface between these server chips that is way more energy efficient and delivers bandwidths that are unheard of. So the idea is a fully embedded optical interconnect that is completely adaptive. That doesn't exist today. There's no optical transceiver that is turned on and off only if bits are needed and is off otherwise. Yes? And then, if we have a server board, now we put it into a backplane. That's the bottleneck. And instead of putting it in a standard backplane, we propose to use a wireless backplane. So that we have these 3D chip stacks sitting here, and the top chip are the antenna arrays. We're doing this at 200 gigahertz carrier frequency, or 180 gigs to be exact. I'm showing that we can do 100 gigabit per second beams and streams like that. And by the way, that is where the zero crossing modulation idea came up from, because we had to find a solution so that we can build something that is less than a milliwatt power consumption to be able to run these beams. And then we suddenly saw we can use this also for cellular communication. So that is the idea, to build this with on-chip 8x8 antenna arrays, and we can talk to all the other neighboring beams. We have a fully connected crossbar switch over the air, which is super energy efficient, because this is what computer scientists want. And since we only turn on the optical and the wireless links, that already gives us 100x power consumption efficiency. Why? Because if you do an InfiniBand analysis of your computers today, they're only on less than 1% of the time. And so the idea is, this is a mix of memory with near memory or in-memory computing engines, and these processors are only activated if that memory part is being processed. And by having these ideas, we think we can gain 100x. And that means we don't go from 200 to 3,000 terawatt hours, but hopefully we can go down and actually build these super cool high-performance computers with less power consumption than what the things you consume today, without whatever kind of scalability, obviously. Here you see what we demoed at the 5G Summit in Dresden last year. Here you see up front, these are the wireless links. In the end, we have the operating system and scheduler systems and everything, showing that we can actually run complex software on this kind of a beast. Obviously, we didn't build this. We just demoed this by emulating links. We build an optical link, we build a wireless link, and we emulate the box, we emulate the whole idea of how such a server looks like, and then can actually check out by simulation if this is efficient as we think it is. So in conclusions, where are we today? I think that's where we are today. If I think of mobile robotics. Yes? Think of it. This is a carriage, the motor strapped underneath, and a crank to steer the wheel. There's no steering wheel, there's no pedal, there's no brake. That's where we are. This is, our carriage is 4G. The motor that we strapped underneath is what is called network slicing, to be able to give service guarantees. And the crank is what is called new radio. That's sort of a little bit of the third wheel with a crank, such that we can have shorter packets and go up to 1 gigabit per second and have massive MIMO. What we really want to drive today is this kind of beast. Yes? Now what is, I think this picture is very important. Why? The company that invented this left guy is still in business. So if you're here early enough, you can be in business 100 years later. So, and we need this. We cannot invent as engineers this right away. We have to take a step at a time. So, yes, 5G is the best thing that can happen on planet Earth. We need it. We have to use it. We have to improve it. But never ever think that this is the end of the story. It's just the beginning of the next wave. Mobile robotics, the tactile internet. So we do need a 6th generation, and we most likely need a 7th generation. The 5G logo, by the way, I think looks a little bit weak because it looks like a flower whose leaves are wilting. To me, I would like to water it a bit. That's why I said this looks more like a rocket taking off. This is not an official logo, the 6G. This is just my own little creation to show you. We need 5G to make 6G happen, yes. That's just the way things are. And that's fun because we as engineers cannot come up with the right solution right away. That keeps us busy, gives us something to do, and gives us a job. So I touched a couple challenges. I touched 8 challenges. We need to go beyond 10 gigs for AR, VR. We need reliability. We need, with using a real old framework from the moon mission, we need control, communication, co-design with a low latency. But what does that really mean? How many packets in a row really can be lost? Oh, now something hops around, sorry. We need to be able to map this scalably onto hardware solutions. So we have to come with real cool operating systems, scheduling, multi-process system on chip designs to do that. We have to start building something that is resilient against intentional jamming. Today's networks are not built that way. Nobody thinks that you can jam a base station. Any kid can do that. But it's no fun today. In future, it will be. And that's why we will see it happening. We have to massively increase the energy efficiency, coming up with architecture solution, as I just showed. This is one way. But we have to map the software, the system, design everything such that we can actually get that 100x improvement. Otherwise, we don't get it. We have to have the security and privacy architecture, and we have to address the global coverage. These are just 8 topics I touched right now, very quickly, without showing any kind of equations and papers and whatever. I could have gone in depth with gazillion PhDs on every one of these topics. Just to give you an idea why I think it's so important to continue on and so much fun to do this. And that's why I think, as a wireless physical layer engineer that I am, I have so much still to do. Yes. If some people say the physical layer is dead, it is not. So here, just for you to see, this is the tactile internet in the taking over your kitchen of the future. This is how Telia Sonera took up the idea, my idea of the tactile internet, building mobile robotics. Sorry, it's a little jerky, but you see this gun with these M&Ms. This is what I want. It should just shoot always some into my mouth whenever I feel like it. But that is how your kitchen looks like if you do it with remote control. So we need a little bit less messiness. Yes, so we do need 5G, and we need to go beyond to really invent this stuff to make this happen. So that's why I also want to thank, obviously, Vodafone for this year. It will be soon 25 years of continued support. That's pretty cool. Thank also Vodafone for this continued support. And thank you.